The goal of today is to talk about an alternative way of doing broadcast, but not in a reliable way, in the sense that we do not expect our protocols that we are going to see today to satisfy the properties that we have seen for reliable broadcast. Okay. Instead, we relax and we describe what is called a probabilistic broadcast, although there are other ways to see this topic, and we try to be able to scale to much larger number of processes, nodes, and so on. Because the idea in reliable broadcast is that the communication is n square, because you have to send a message to every other node, and everybody has to send a message to every other node. And so this doesn't scale very well when you have like hundreds of, or thousands of participants. So the idea, we'll discuss about the motivation. I will give you what is the system model that we are going to use, specification, and some theory about epidemics. And then we will look at algorithms. One is the best effort, again, just to have a way to compare them. And then anti-entropy, rumor mongering, and then we will deal with some details like deletion and death certificates, but we'll see it's not really very important. The principles are discussed here in these two parts. Okay. So, application level broadcast, multicast, as we said, is an important building block for distributed applications. It is important if you are trying to to create some sort of consistent service, a replicated service. But it's also important when you do applications that have more relaxed goals, like video streaming. So the idea is that currently, although this is done centrally by Zoom, my packets are distributed to all the participants in a broadcast way. Maybe you are losing some of the frames, but this is not really important, because the idea is that you can deal with that. Maybe there are a few milliseconds of lag, but that's okay, because we are trying to do our best with this kind of system. So if you have several participants, Zoom can deal with up to 300 participants, but then there is the webinar option with up to, I think, 10,000 or something like that. Ideally, we like systems that are efficient, robust, and also quick when they scale, okay? And the approach that can be taken to the problem of data dissemination are more or less three approaches. One is flooding, which is the reliable broadcast approach, which is really robust because you can processes my crash at any time, but still it is able to let every node to get the same information, but is inefficient on square. Then the other approach that we are not going to look at it very much, apart in the peer-to-peer area, is tree distribution. The idea is that you create some sort of hierarchy, and there is a root that sends to their to its children, and the children send the packets to the grandchildren, and so on. This is very efficient because at the very end only n order of n messages are sent, but it's very fragile. You crash one node and part of the tree is disconnected. And then there is gossip, which is the topic of today, gossip or epidemic protocols. And it's both efficient and robust because the number of messages that are sent is in the order of n log n. It is robust because we can tune the probability that we want to to obtain the probability we want to satisfy with respect to message delivery, but tends to have a relative high latency, so it's not really quick, or the speed is not so good. And we are going to measure scalability based on the total number of messages that we are going to send. So when you see n log n, it means that every node on average has to send log n messages to the other nodes in order to complete the protocol. And when you see order of n, means that every node on average has to send a message to a constant number of other nodes. And then we look also at possible imbalances that are present between nodes, which means that we would like to avoid a really centralized approach where a single node has to send a message to everybody else, which is actually the case of Zoom. We are looking at other models. So this is a slide of Robert van Rennes from Cornell University. The general idea is that you can remember which is good, which is bad by this figure. And so if you want to use a tree, you get fast and efficient, but not robust. If you want to use flood, you get fast and robust, but not efficient. If you use gossip, you get efficient, robust, but not really fast. Sometimes you can see combination of these approaches, like I have a tree, and the tree normally works very well, but I have also a parallel approach based, for example, on gossiping. And the idea is that the tree provides a very good service on normal condition, and the gossiping, which is slower, provides a good service when there are problems, failures, disconnections, and so on. So if you remember the first lecture, I was talking about the possibility using probabilistic approaches to solve distributed system problems. The first example was very silly, the idea to send several messengers in two general problems. Okay. Here, at the very end, the approach is the same. You are sending several messages, but you tend to distribute them to other nodes. And the terminology that we are going to use, you already guessed it, is based on epidemics. So now we are all experts of epidemics, but when I started to do this lecture, this is not something that everybody knows, or gossip, because at the very end, epidemic dissemination is the same principle which is behind the diffusion of news between people in social networks. Okay, and the idea is that we want to reduce the number of messages, clearly less than n squared. And we like to avoid that no single node is overloaded. But we will get probabilistic guarantees and not deterministic and 100% guarantees on our delivery. So the first use of the word epidemic and gossip is by Alan Demers in 1987. But at the very end, some protocols like an NTP, which is a very old news diffusion protocol, was based on similar ideas. And you will also see similar approaches in networking systems that are not as robust as the wired internet. So, for example, in IoT networks, in ad hoc networks where nodes connect each other in a very peer-to-peer way, in delay-tolerant network in which nodes are not constantly connected, but you may have, for example, nodes on buses, real buses, and the buses go around and move information. in areas where cellular networks and wired internet is not available. All of the systems which are limited in their capabilities can use approaches that are based on the ideas that we are going to look today. But in general, the problem started in a completely different setting, wired internet with a collection of replicated databases. In the 90s, the gossip approach was applied and optimized for the information dissemination problem. During the beginning of this century, a lot of researchers, including myself, realized that gossip can go way beyond dissemination. And so we will see, not today in another lecture, other applications of gossiping in area which is not just send messages around. 2006, there was a work on the future of gossip, and even today I'm part of, actually, I was supposed to be in a meeting at this very moment about a workshop on decentralized distributed systems, which is the area in which gossiping protocol give their best. Okay, so I give you this very old scenario. So there was Xerox, a very important company in the computer science area in those years. They had a database replicated thousands of nodes. These thousands of nodes, if I remember correctly, were machines accessed by representatives. So the idea is that you want to share some information like prices of products or stuff like that to all the copies of the database. You had, at the time, you still have a heterogeneous and reliable network, and updates to single element of the database could be injected at multiple nodes. And those updates must propagate to all nodes or be supplanted by later updates of the same element. Okay, so the point is that maybe I change one line of the database and you change another line of the database, and I do this in one copy, you do this in another copy. For a moment, the two copies are not consistent. The dissemination process starts, and eventually, prima o poi in Italian, the copy will become consistent, unless there are other updates. And so it is perfectly possible that the system is not consistent at any time because there is a continuous flow of updates. But assuming a reasonable update rate, most information at any given replica can be considered current. Okay, and this is the approach that is used not anymore just on a system like this, but also in more modern system. For example, Amazon used a gossip protocol to quickly spread the information throughout their S3 system, which is not our S3, something better, as you know. And the idea is that, and this is something that in some very old projects for the course we were able to actually measure. If you inject a change on S3 bucket, so in a piece of storage that Amazon is giving you, and you try to assess the same piece of information from a completely different system, you may access another copy of the bucket, and for a very small amount of time, in the order of less than 1 second, the two copies may be inconsistent. Okay, but this is perfectly fine for the kind of application that are run over S3. Dynamo, which is another internal service of Amazon, is based on gossip-based failure detection, and we'll see later what is a failure detection service. There are open source key value stores like Raya, Cassandra that are based on gossip protocols, although Cassandra changed over the time their approaches. The basic information exchange in BitTorrent is based on gossip. The idea is that we are distributing pieces of videos, files, music, etc. in that way. And I forgot to add the mechanism with which blocks are disseminated in Bitcoin and similar system is again based on gossip. Okay, so basic assumption, the system is asynchronous. This is another case in which we can deal with asynchronicity, and there are no bounds on messages process execution delays. Actually, the more unreliable the system is, also respect to time, the better motivation we have for systems like gossip. Process failed by crashing, so they stop executing actions after the crash. Today, we do not consider Byzantine failures. Later, we will show you a Byzantine-based gossip protocol. Okay, and communication is subject to benign failures, which means that you can lose messages, but there is no message corruption, creation, or duplication. And this is perfectly okay for the kind of system that you want to implement over using these processes, which means that, for example, you may want to authenticate in some way the nodes that are sending message around, otherwise you cannot really guarantee no corruption. Now, the data model. The data model is first very complex, then we will simplify to focus on some principles, and then later there will be a discussion about how to actually implement these kind of systems beyond the very simple protocols that we'll see here. Okay, so we have a database that is replicated over a set of n nodes. At this point, we consider these nodes, this set of nodes, well known to everybody. So everybody has the same view of the entire system. We will relax this later. The copy of the database can be represented by a dictionary. So an association between keys and values. Plus, there is this time varying aspect. So the idea is that you are associating keys to values and their timestamp. So you can recognize which value is younger or older than another value. So the idea is that when you want to update value, like here, you write, update the value associated to a key, K, you update the value V, and you associate some sort of timestamp, which is globally unique and is enough to distinguish between information which is newer or older. The goal of the update distribution process is to drive the system towards consistency. Eventually. In fact, it's called eventual consistency. If no new updates are injected after some time t, eventually all correct nodes will obtain the same copy of the database. So every node, PI or PJ, for every key in the database will have the same value associated. Okay? And value in this case means the actual value and the timestamp. Okay. And another view of this the system is trying to define a broadcast specification. So we go back to best effort, but because there is no agreement here, so this is not definitely a reliable broadcast. And we say that there is a given probability such that for any two correct nodes P and Q, every message PB broadcast, probabilistic broadcast by P, is eventually PB delivered by Q. And that given probability can, in some cases, be computed and is well known, okay? Or may not really be computed, depends on the underlying condition of the network as a function. But the general idea is that you will see that the probability can be made so, the probability of failure can be made so low that you can consider them as practically reliable. And integrity is the usual integrity. So we have, as I said, we have no agreement property, and probability in best effort broadcast is hidden in the process life cycle. So it is possible that you do not deliver a message, but depends on the network condition and the status of the process. Probability in probabilistic broadcast is explicit and potentially computable. And as I said, there are some simplifying assumptions, okay? And the assumptions are as follow. Every node knows every other node, so they are able to communicate with every other node. The communication cost between nodes are homogeneous, which doesn't mean much today, but there was potentially a problem a lot of years ago. But in general, it means that in order to send a message is substantially for free everywhere. And to simplify the notation, we assume that there is a single entry in the database, so there is a single key. So we look at one key at the time. So the specification is based on one key at a time. So when we say value of key, this can be simply written as value, and the time since is denoted value.time. And managing multiple keys is actually a little more complex than just adding for each key do something, because you may be bandwidth constrained, so you may do not want to send some of the keys with respect to the other. But all these assumptions will be relaxed later, and so we start with something really simple today. Okay, so epidemiology, as we know now, studies the spread of a disease or an infection in terms of populations of infected and infected individuals and their rates of change. So the famous now R0 parameter that tells us how many people are infected by a single infected person is part of the definition that are behind epidemiology. And as we know, we want to understand if an epidemic will turn into a pandemic, and we want to adopt countermeasures to reduce the rate of infection, inoculation, isolation, masks, gloves, and lockdowns, and whatever, okay? But this is for diseases. We look at this in a more positive way. Instead of trying to stop the spreading of information, we try to enhance the spread. So sorry, instead of stopping the spreading of viruses, we try to enhance the spreading of information. And in epidemiology, the oldest and the most cited model is the so-called SIR model by Kermack and McKendrick, which is as old as 1927. Okay, and the idea is that every individual, every node P can be susceptible if P has not been yet infected by the disease, infective if P is infected and capable to spread the disease, and removed if P has been infected and has recovered from the disease. And normally, in the basic model that we are going to consider, you have these kind of arrows. So you go from susceptible to infected and then to removed. But they may have much more complex way of modeling the epidemiology situation. So for us, how does it work? Initially, a single individual is infected. Individuals get in touch with each other, spreading the disease. Susceptible individuals are turned into infected ones. Eventually, infected individuals will become removed. And this curve here, which is the famous curve to be flattened, is the amount of active cases that are at some particular case. So infective people at some particular point. Initially, everybody is susceptible, which means that apart from one, they tend they are not touched by the disease yet, and then potentially, if the process goes on until the end, they go to zero, okay, and the number of infected, removed people goes to 100% eventually. Okay. There are, as I said, there are other models, like, for example, the Sears model, SIRS model, in which it looks like coronavirus could be like this. After being removed, you may go back to the susceptible state, okay? And then there is the Sears model, in which you can be exposed, but not yet infective, and so on and so on. You can be dead. There are several states that you can reach. And as I said, we want to go from epidemiology to distributed systems. So we want to spread information as quick as possible. Okay. And we applied the mathematical models that are behind virus spreading to information spreading. And given that we were talking about database replication, the SIR model is now like this: susceptible if P has not yet received an update. Infective if P holds an update and is willing to share it. Note that willing, it means that you may want to stop spreading an update because you have an amount of bandwidth that you cannot waste. Removed, you have the update, you are happy with that, but you no longer are willing to share it to other nodes. Okay, rumor spreading or gossiping works on the same principle. And now, after a lot of motivation, we start to talk about our algorithms. So 10 seconds of best effort again, and then we focus on anti-entropy and then on rumor mongering. And then we will turn what we got for databases into a probabilistic broadcast. Okay. So this code here, just to remember what you can do when you receive an update. Okay. When you receive an update, the direct mail approach is the term that you find in the original paper, okay? And what you do is to notify all other nodes about an update as soon as it occurs. And when you receive an update, you check if it is news. If it is news, it is the more up-to-date information that you have, then you update your local copy. And so when there is an update here, you just send the update and the value. The value, as you see, contains both the actual value and the timestamp, okay, to everybody. And then when you receive an update, you get a value and a timestamp. You have a local value, okay, and if value.time is smaller than t, it means that this update that you received is new, and then you update the local information. As I said, this is very simple. It's not very difficult. It's the basic protocol that you can use.